Welcome to Maths with EJD. In this video, our focus is now turned to prove. We want to prove that 1 squared plus 3 squared is the square of odd numbers, the sum of the square of odd numbers, right? Plus 5 squared plus all that plus 2n minus 1 squared is the same thing as n into 2n minus 1 into 2n plus 1 all over 3. Now, this is all over 3, right? For all positive integers. For all positive integers. Okay? So this is one of those cases where you already know the answer to get at the end of the day. So the answer should be such that for every n, you have k plus 1. So you should have k plus 1 into 2 into k plus 1 minus 1. For this now, 2n, 2 into k plus 1 minus 1. Then again, 2 into k plus 1 plus 1, all over 3. So you already know the answer you should get from the very beginning, all right? So that is that. That is what we're working towards. So it's always good when you already know where you're going to, right? So when you get there, you definitely know. So let's take our normal procedure. Let's follow our standard procedure, So first, let's talk about the claim. What is the claim we are dealing with here? The claim is that 1 squared plus 3 squared plus 5 squared plus all that plus 2n minus 1 squared is the same thing as n into 2n minus 1 into 2n plus 1 divided by 3, for all n greater than or equal to 1, for all positive integers, right? So next we move on to talk about the base step. The base step is where you use the smallest possible values. So, and the smallest possible value for a positive integer is n equals 1. So at n equals 1, right, the right-hand side again is a sum. So for sum, you sum things up. The right-hand side is a formula. For formula, you substitute values, right? So at n1, so LHS, the left-hand side is actually 1 squared, which is 1. And the right-hand side is 1 into 2 into 1 minus 1 into 2 into 1 plus 1 all over 3. And that is 1 into 2 times 1, 2 minus 1, 1 into 2 times 1, 2 plus 1, 3 all over 3. So 3 cancels, and then you still have 1. So you see the left-hand side and right-hand side. So left-hand side is equal to right-hand side is equal to 1. Okay? So let's take it further. So at n equals 2, right? At n equals 2, what happens? So since you are summing, you have to sum these two together. So you have left-hand side is 1 squared plus 3 squared. And that is 1 plus 9, which is 10. But then the right-hand side, you substitute n. That is 2 into 2 to minus 1 into 2 to plus 1, all right, all over 3. And that is equal to 2 into 2 times 2 is 4 minus 1, that's 3, right? And then here you have 2 times 2, 4 plus 1, 5, and that's over 3. So this cancels out, and you still have 10. So you see again that the left-hand side is equal to the right-hand side, and that is all equal to 10. So that's the base step. So you can say, therefore, the claim is true. The claim is true for the base step. The claim is true for the base step, like that. And then we move on to the inductive hypothesis. The inductive hypothesis. So for the inductive hypothesis, all you do is assume. So assume the claim is true. Assume the claim is true for n equals k. That means you just have 1 squared, right? Yeah. You just have 1 squared plus 3 squared plus 5 squared plus all that plus 2n minus 1, right? Yeah. 2n minus 1 squared. That is 2k now, 2k minus 1 all squared is equal to k into 2k minus 1 into 2k plus 1 is equal to k into 2k minus 1 into 2k plus 1 all over 3. So don't forget, at the final stage that I like to call the final showdown, right? That's the inductive step. You already know the answer you should get. It means for every k here, you should have k plus 1. So that's what happens at the inductive step. So at the inductive step, now what do? We want to prove that the claim is true for n equals k plus 1. Okay, so that means we have 1 squared plus 3 squared plus 5 squared plus 2k minus 1 squared. Now here it becomes a bit tricky, so pay attention. So plus 2 into, instead of k now, sorry, this should be plus 2k. Instead of 2k, you have 2k plus 1 minus 1, Instead of k, you have 2k plus 1. So squared. And since this is equal to this, so anything you add to the left-hand side must be added to the right-hand side to balance the equation, right? So you don't do, it's not like you're going to now change all the k's here. No, no, no. So you add the same thing you have added here to the right-hand side and then solve until you get what we expected to get. So here you have k into 2k minus 1 into 2k plus 1 all over 3 plus this thing, this particular expression, and that's the only way the equation, this is equal to this already. So if you add, whatever you add to the left-hand side must be added to the right for them to be the same. So I know this is where a lot of people miss it. You may just think you also need to add k plus 1 and all that. No, no, no. You add exactly what you added to the left. So, and that is, say 2 into k plus 1 minus 1 all squared. You can put that over 1 now. So now this is what you solve until you get to the final result. So I'm bringing this down here. So I have k into 2k minus 1 into 2k plus 1 all over 3 plus, so now you can tidy things up inside there. So you have 2k plus 2 minus 1 all over 1, or, all that squared, right? 2k plus 2, so that this is equal to k into 2k minus 1 into 2k plus 1 all over 3, then plus 2k plus 1, 2k plus 1, right? 2 minus 1 all over 1, this squared. So, I mean, we're already beginning to see a pattern. So you can see the LCM is 3 straight up. So LCM is 3. So 3 and 3 is 1. Multiplied by that, you have k into 2k minus 1 into 2k plus 1. All right. Plus 1 in 3 is 3. So you have 3 into 2k plus 1 all squared. Now, what are we expected to get again? Don't forget, what we expected to get is k plus 1 into 2 into k plus 1 minus 1 into 2 into k plus 1 plus 1 all over 3. That's what we expected to get at the end of the day. So let's see how that works out here. So we can already see that 2k plus 1 is common. Let me change the marker at this point. Let me go for this. So you have 2k plus 1, 2k plus 1 into 2k plus 1 into k into 2k minus 1 plus 3 into 2k plus 1. Okay, so, and all of this is over 3. So it means we have to tidy up inside. You have 2k plus 1 into 2k squared minus k plus 6k plus 3 all over 3. That's k times k, 2k squared, k times minus 1 minus k, 3 times 2k is 6k, 3 times 1 is 3. Then we have 2k plus 1 into 2k squared plus 5k, that's minus k plus 6k, that's plus 5k plus 3, all over 3. So now we need to factorize this. So let's take that aside and deal with it. Okay. So you have 2k squared plus 5k plus 3. All right. So you need two numbers. When you add, you get 5. When you multiply, you get 2 times 3, which is 6. Which is 6, right? Two numbers add, you get 5. Multiply, you get 6. And they need to give you 5, positive 5. So automatically, it looks like that should be 2 times 3. That's 2 times 3, 6. So fact that there should be factors of this. That's 2 times 3, all positive. So here we can come back and say that so let me change the marker again. So this is 2k plus 1 into, okay, maybe not yet, into 2k squared plus 2k plus 3k plus 3. 5k is 2k plus 3k. So all this over 3. And then we have 2k plus 1 into 2k is common in the first one. So you have 2k into k plus 1 plus 3 into k plus 1. All of that over 3. Now we still go on and we have, so you can see k plus 1 is common inside here, or we can just say that, so you can take 2k plus 1 out straight. Let's just take that out. K plus 1 into 2k plus 1 into 2k plus 3 all over 3. So now what was the original expression we had on the right hand side? That will be our compass. We have k into 2k minus 1 into 2k plus 1. K, so that was k. So what we had was k into 2k minus 1 into 2k plus 1 all over 3. So this is serving as our guide. For this k, we have this one now. So I suspect that this 2k minus 1 now, so it has to be something. So we need to have, this is supposed to now be 2 into k plus 1, minus 1. That is what it's going to translate to here. And that's the same thing as if you multiply this out, you have 2k plus 2 minus 1. Now, so you see 2 minus 1 is 1 already. And that means that is going to happen for this place. So it means 2k plus 1 can be expressed as 2k plus 2 minus 1. So that's that. Then for this side also, it's obvious. We can easily express this as 2k plus 2 plus 1. So, okay, I guess I can also change. Let me go all black now. So we have k. So this is k plus 1. So here you have 2k plus 2 minus 1, because 1 here is 2 minus 1, and then here you have 2k plus 2 plus 1 all over 3. So now we can factorize. So we have k plus 1 into 2 into k plus 1 minus 1 into 2 is common again. So you have 2 into k plus 1 plus 1. All this over 3. And then you can see that it's looking exactly like that. So for this k now, you have k plus 1. For this 2k, you have 2 into k plus 1. Of course, minus 1. For this 2k plus 1, you have 2 into k plus 1 plus 1. So with this now, we have all we need. And that is it. So that is all we need. So this is exactly what we need. So we can conclude now that we have arrived. So in conclusion, since the claim is true for the base step, and the inductive step, it is true for all positive integers. So on this note, if you have not subscribed, be sure to do that. Hit the notification bell so you can get alerted when a new video is released. So like, share, comment. If you need us to solve a problem, please feel free to talk about it in the comment section, and then share with other people that will need it. See you in the next video.